that's all from my side. I would like to introduce the first speakers. So cooperation is what the Cluster Exchange Program is looking for, and it's looking to promote. And the promotion of the market access of innovative technologies in energy sector is one of the aims, as I said, of the Smart Energy project. Today's session is dedicated to the discovery of some cooperation projects on hydrogen technologies that we think represent some successful examples, not only for their outcomes, but also or for their expected results, because some of these projects are ongoing projects, but also good examples of cooperation between different actors of our regional ecosystem with partners also from regions, and some of them also represent good examples of the role that regional clusters can have in supporting the construction of projects and innovative projects, and in particular to support their members on these kind of processes. But also we have some examples of the importance to have public and private partnership. Most of these projects you see are funded in particular under the FCH-JU program. We will see what this program is to facilitate market introduction of fuel cell and hydrogen technologies in Europe through European dedicated resources. So this is the today's aim. What we would like to look more in detail. So very different projects. Some of them involving some of the actors and players that already was presented in the first webinars, but with a common aim to bring hydrogen technologies to make, I would say, one step ahead in terms of development, demonstration, and finally also market access. So the first project is the Demosoft project, which is an example of cooperation between technology providers, research organization, and a multi-utility company. It's a regional multi-utility company from Piedmont region for the development of a demonstration plant based on the use of fuel cell for an innovative valorization process. So I leave the floor to Professor Massimo Santorelli for his presentation. Massimo, please, it's up to you.
Oh, thank you, Luca, and so good morning, everybody, to the audience. Thank you for inviting me to this interesting event. I see a lot of friends also in the speakers and colleagues. So I can share my screen. I think now I have the possibility. Yeah. Okay. I think you can see it in presentation mode. Is correct?
Yes, we can see it.
Okay, fantastic. So I will. I have just to reduce. Okay. I will present, as you see, an experience that we have done inside a European project. So it's a collaborative project, as you said. Is related to the use of high temperature fuel cells, so fuel cell that work with ceramic materials at high temperature. Because of this, in connection with renewable fuel, which is a biogas. So I will explain this experience, which is a real experience in an industrial site. So after, let's say, 20 years of work on at the lab level and on some demonstration project, we are arrived to the level of a demonstration of this technology at the industrial level. So this is one of my of the activity that I'm most proud, because it is in some way a result of the last 20 years of activity. As you see, there is a list of partners. In fact, is a partnership. Politecnico di Torino, in which I am a professor, is the coordinator. We have worked with a company in Finland, which is called Convion, which is the provider of the technology at this industrial size. The collaboration has been very good in Italy, in Torino, especially with SMAT group. So the group that the company municipal company that manage the waste and the water in the municipality of Torino. A very good collaboration, I can say. And then the other two partners are the VTT, the Research Center in Finland, and the Imperial College in London. Okay, so I go to the point. Here I show you a picture. It's the same of the other slide. A picture of the installation that we have done in Collegno, which is a municipality in the border of Torino. Is 20 minutes from where I'm talking
Marco.
now. Hello. Sorry, I have a voice. Sorry.
Was für ein Spruch?
Hello. With a microphone. Okay. So it's a municipality in the border of Torino. It's 20 minutes from the point where I am now talking. It is a project that's been financed by the Fuel Cell and Hydrogen Joint Undertaking in 2015. And we have worked for 5 years until, well, it's still operating, but the project is going to be completed. And you see, it is the way to combine a renewable fuel, which is a biogas from the wastewater treatment plant, with the best way to make use of this biogas from the energetic point of view. So if the aim is to produce electricity, for example, there is no other technology which is better than a high temperature fuel cell, a solid oxide fuel cell specifically. And we have done that at the level of an industrial plant. The plant is not so big in general, in absolute, because it's a 110 kilowatt of electrical energy and a recovery of 55 kilowatt of thermal energy. So it's not a huge plant, but at the moment it's the biggest plant in Europe that utilizes this technology. And I think, for what I know, also at the international level, the combination biogas plus solid oxide fuel cell, I think, is still the largest plant in the world. There are other examples of this type of plant, mostly in California, but are or using molten carbonate fuel cell or using another type of fuel, which is natural gas, which is not a renewable fuel. You see, I'm talking about efficiency. The efficiency is electrical efficiency I'm talking is very high. So I will show you the result, but we are moving between 50 and 50, but even more. We have reached 58% of electrical efficiency from biogas to AC electricity. I mean, at this size, especially, is an impressive result for people that are expert on, electrical production. This is the plant. The plant, of course, has been installed in a already existing wastewater treatment plant. We have not built the wastewater plant, but the solid oxide part. So there is from the gas holder on, there is the new plant you see in the schematic. So first we have to treat the biogas, because the biogas contains contaminants that can contaminate the catalyst of the fuel cell, of the anode of the fuel cell. So there is a first biogas processing system that I will show you. And then there are the fuel cell, the 3 module of fuel cell. I just say that at the end we have been able only to install 2 modules and not 3. It's a long story. I mean, it's not significant for today. So in place of 3 modules, we have 2 modules, but the concept is the same, producing electricity at high efficiency. And all the module, there is a recovery of power, of thermal power. As you see, the thermal power is given to the there is a first loop with water and glycol-ethylene that exchange with a secondary loop in which the heat is then given to the sludge before going, you see, to the digester. So the heat is recovered in order to preheat the sludge, which is a necessary activity in a wastewater treatment plant. So you see the energy recovery is complete. This is the picture, a top view of the plant. As you see, is a classical wastewater treatment plant. In it, you can see the gas holder. You see here on the top. So there is the gas holder. On the bottom, you see on the bottom in the left, there is where we have placed the fuel cell plant. So you see there is this line, the green line, that in which we have to distribute to transport the biogas. I mean, the logistic has been obliged by the morphology of the plant. So this long distance has been due to the local situation. Then the fuel cell also use compressed air for the operation produced here, and And finally, there is the electrical connection with the grid interface internal to the plant. I can say that all the electricity is used inside the wastewater treatment plant. Economically, it's better to self-use the electricity producer compared to exchange with the grid. It's only an economic balance, depends on the local rules. In Italy, it is better to self-use the electricity inside. But I mean, the consumption was enough to, to absorb all the electricity produced. And then there is the hot water that has been produced as a recovery, as I said, to preheat the sludge. I show you some pics about the evolution of the work, because we started from scratch. It's a real industrial, installation. So it's a good experience. A fundamental experience for the future, I think. So we started from this green field, as you see. So this was before the fuel cell. Somehow I can say it was better, but yeah, the technology was the only place to place the technology. And then we have built the basement. You see, is a concrete basement in which there are all the connections which are underground. It's very elegant, also a little expensive, as I will tell you. And then the piper rack to transport the biogas from the gas holder to the fuel cell, you see here. And finally, the technical building, you see the technical building for the control, the first module of fuel cell. This is the module for the cleanup of the gas. So you see some aspect of the work when we built the system. As I said, the biogas, of course, is a good fuel because it's renewable and contains a high molar fraction of CH4. Still, it contains contaminants, of course, coming from the biological sector. The worst, the contaminants that can be more dangerous for the catalyst in the anode are basically the sulfur compound, mostly H2S, and the silicon compound, so the siloxane. And you see, in average, we can have in this biogas an average of 28.66 ppm of H2S, quite good, quite low in terms of content of contaminant, and around, in average, 4 milligrams of silicon per silicon equivalent per cubic meter, with a peak of around 10. So these are the values that we have to deal with. Of course, they change during the time, during the year, because of the variability of the meteorology. But anyway, you have this value that you have to deal with. So, and to deal with in which way? You see the target of the solid oxide are very strict. Somebody can be, impressed. So you see for H2S is 30 ppb, so part per billion. And for siloxane, even worse, 10 ppb. So it means 0. So it means to be totally cleaned. Yeah. I have a lot of experience in the lab level that I can say that for the classical anode of solid oxide can resist to around 1 ppm of sulfur without degradation, without structural degradation. Anyway, the target was very, very strict in order to not fail this big demonstration, simply for a problem of contamination. So these strict targets are have to be reached because of the importance of this plant, but can be relaxed. Okay, so in this is the contamination structure that we have planned, and then we have designed and then constructed with a company in Italy. So first, there is an already existing possibility of the separation of the water with a gravel filter in the smart side. It was already included. From now on, we have done the contamination system. So first, it is necessary to separate as much as possible the water using a chiller, because the water is competitive in the absorption side that we have used downstream. So absorption, we have used absorption to separate this type of contaminant. So first we have separated the water using a chiller. Then you see the rest is called lead and lag configuration using activated carbon dedicated for the separation of sulfur from one side, the silicon, organic silicon from the other side. So there are, you see, two vessels in series that separate sulfur and silicon, and then there is some point of measurement in terms of quality of the gas that suggested to us to have or not a shift. When we use in the measurement number 4, you see here, that the contaminant has slip across the bed, we make the lead and leg. So we switch the lead to the leg. So the leader become the leg, and the leg become the leader. Sorry. So this is to assure a continuous operation. You see here where the picture of the vessel containing the carbon that we have designed as Politecnico and built with a company in Italy called Biocomp. And you see here there is the container containing all the system for the decontamination of the gas. So the gas at the end go clean to the anode of the fuel cell. Here is an interesting aspect. This is the electrical connection to the grid, internal grid of the wastewater treatment plant. So you see where are the fuel cell, which are connected to the low voltage line internal to the site. So you see there is also a connection to the external medium voltage line, but as I said, we never used it for economic reason. And then, of course, the power is distributed to all the system. This is normal. The interest is the second one, because in case of a blackout that can happen, I can say it can happen frequently in a situation of a wastewater treatment plant, because usually a wastewater treatment plant usually is not in the center of a city, fortunately. And so it is usually in a borderline, in a border point of the line. So I can say that the blackout are quite free. I mean, more frequent than in other normal part in a city. So this is good, because the machine is good. The fact that the machine, the solid oxide, can go in operation in island. So it's possible to go in island in case of a blackout. The machine go on to work. Of course, there is the biogas, and they can supply the electrical system in island. It has been very appreciated by the end user, I can say. So it's a good point to outline in this type of presentation, I think. Thermal recovery, as I said, is a complete recovery using water and glycol ethylene as a first loop. So the gas are exhausted at around, you see, 200, 250 degrees. So we can, at this temperature, it's interesting, we can do a better use, a good use of this high level of thermal energy, because it's not 50 degrees, let's say it's 200 degrees. Still, the interest in the plant was only, let's say, to produce, to preheat the sludge, as I said. So at the end, we use this 200, 250 degrees to preheat the sludge from 45 to 70, the water, and then the sludge. So we preheat the water from 45 to 70 degrees. So you see there is a thermodynamic gap, but yeah, it is justifying this type of use. So we preheat the water at 70 degrees, and then the water is used to preheat the sludge at 40 degrees for using the sludge to make the digestion in thermophilic condition. So this is the recovery. I show you some details, the pump for the circulation of the water plus glycol. And here you see the tube and tube heat exchanger, where you see in this one, in the bottom, there is the tube and tube heat exchanger where we make the exchange between the water plus glycol and the sludge that are preheated. All has been done from scratch. Summary, so we go to the result. Decontamination. Decontamination, you know the value that we started from, around 50 milligram per cubic meter in H2S and 4 milligram per cubic meter in siloxane. This was being the average in the year in which we used in the 3 years that we used the machine. The result of the decontamination, 0 sulfur and lower than 0.1 milligram per cubic meter of equivalent silicon below the detection limit, let's say. So this so the contamination was okay. Electrical result. So here we have a module. You see the module can operate in power. So this is the power, 40 kilowatt, 50 kilowatt. You see that it can modulate. So it's not a machine that is fixed in a given point. It can also modulate. This is important to say. And these are some tests. You see these spikes are not spikes. These are some tests that we have done in order to put the machine in island mode. So these are tests that we have done voluntary. So in order to test the capability to the machine to go in island mode that I described before. So the machine, you see, work also in partial load. And the important is the result. So the result, the machine, I always talk of one module, just as an example. So you see the around 77% of the time it worked in nominal point, so between 50 and 55 kilowatt of theoretical power. So you see here. In terms of efficiency, you see that for the 79% plus 2, I can say 81%, it worked above 50%, so 79 of electrical efficiency. 79% between 50 and 55% of electrical efficiency, I repeat, from biogas to AC electricity, okay? And 2% of the time it worked between 55 and 60%. The top that we reached has been 58% of electrical efficiency. I can say everybody of you that is expert of electricity production knows that from biogas in an internal combustion engine at this size, I'm talking of 50 kilowatt, the best that you can reach is around 40% if there is a very good machine, 40, 42%. Here we are talking of above 50 with peak of 58, okay? Sensitivity to the CH4, another good point, because this machine, you see, this is a graph in which there are the percentage of CH4 in the biogas that of course change during the year because of the meteorology, because of the climate, external climate, and so that have an effect on the biological process. So you see, this modification of CH4 content usually can be very, impacting in the classical thermal machine. As you see, in an electrochemical machine like this type of fuel cell, the impact is very, very limited. So basically, the efficiency is maintained also with different change in the value of the CH4 in the fuel. Emission. So this is important for the future, of course, and especially if we are in a application which is close to a municipality like Torino, which is very polluted, as we know. So you see, this is the measurement done at the chimney. So it's not a model or something for calculation. It's a measurement in the chimney. These are the list in the table of the most of them are below the detection limit, but I don't go in the detail. But I can say that there are no contaminant, no sulfur, no nitrogen oxide, because there is no combustion, and so on. And I want only to outline the particulate. So you see this graph where there is the particulate concentration versus the size. And you see we have put it in comparison the emission from the chimney, you see the gray one, from compared to the particulate in the air that we breathe around the machine. So the black one. So you see that curiously is better to breathe the exhaust from the chimney of the fuel cell compared to the air around it. So this is of course depends from the fact that the air is filtered before going to the inside the cathode of the fuel cell, but it is an indication of the fact that this exhaust from the chimney are very clean. The costs are not low, of course, as a new technology. It is the first experience at the industrial level. So I report here the list. I'm very honest. I report here the list of the in detail of the costs that we have done in order to prepare the site: mechanical work, electrical work, cleanup, and the total of 853,000 euro for the installation of this plant of around 110 kilowatts, which is a lot. But we learned how to do in the second in a second experience. Now we know that we can do better. We can save a lot of cost in several parts of the plant, and this is the result. We can save 63% of the cost in the mechanical work and so on. We can save in total. Now we know how to save 56% of the cost to prepare a site to host a fuel cell like this one. So we can go to, after this experience, to produce to install another plant with less than half of the cost. Of course, this is important to make your collaborative project, to learn and to do better, to do in a second experience, in the second, third, and so on experience. Okay, the future. So in terms of coverage of the wastewater treatment plant is not so big. You see, in terms of electrical coverage, is 22% of electrical consumption. It's not a limit of the fuel cell, of course, because the fuel cell is a machine that works with the fuel that it has, no? that it receives. So the fuel was the limiting factor. So the biogas production was able to produce enough power with this fuel cell. And I repeat, the fuel cell is the highest efficiency machine that you can use. So if you use an internal combustion engine, you will produce less power, no? So the biogas available was used, I mean, enough to cover 22% of the electrical consumption inside the plant. So the point is, or to produce more biogas with higher merceology, and on the other side, to reduce the consumption inside the wastewater treatment plant. There are, of course, both approaches that we are investigating for the future. Anyway, in this plant, this small plant in Collegno was able, thanks to the fuel cell, to recover around 70,000 euro per year of saving. How to be competitive? Because the fuel cell, of course, still cost. And so I reported here the graph of the electrical efficiency of a classical internal combustion engine. You see here, of course, it increased with the size. You see, going to 100 kilowatts or 1 megawatt and so on. But you see the efficiency is around 42% electrical efficiency. This is the efficiency of a solid oxide fuel cell. This is the area, the range of efficiency between 50 and 60%. Okay, so this is where the fuel cell is. This is the cost of electricity produced by a internal combustion engine using biogas. So you see, of course, it depends on the size. 100 kilowatt is around 0.123 euro per kilowatt hour. 1 megawatt is less, 0.094 euro per kilowatt hour. Okay, this is the situation with an internal combustion engine. So how much has to be the cost of a fuel cell, cost per kilowatt, so the unit cost, in order to become competitive with the internal combustion engine without any subsidy? Okay, this is the result. The cost has to be, as you see, around in a range between 3,000 and 3,500 euro per kilowatt. So we are not so far. Now the cost of this machine is around 5,000 euro per kilowatt, and even less, because Mitsubishi in Japan is able to produce a fuel cell of this kind of at a cost which are around 4,500 euro per kilowatt. So we are not so far from the parity, and we are talking of a technology which is, I mean, quite brand new. There is not a market. So already now there is a gap to recover of around 1,500 euros. It's not so much. So I have a very good expectation for the future of this technology in this type of application. How much can be? Only in Europe, and only considering wastewater treatment plant. So you know that I'm not considering all the biogas sector, which is huge compared to the wastewater treatment plant. I'm not considering all the other applications, only considering the using this machine in wastewater treatment plant producing biogas. We have a potential application in Europe of 2.5 gigawatt. So it's a early market, yes, but it's a huge early market. So there's a large possibility to install this type of system in place of the internal combustion engine in the coming years. Finally, I show you a video of this. I hope you can see. So I don't know if you hear the voice, but I can talk in the video. So this is the wastewater treatment plant. This is the solid oxide. Yeah, top view, you see the plant that we have built. So the first industrial plant in Europe, as I said. Yeah. Oh yeah. So you see the pathway of the biogas going to the fuel cell, the production of energy. So around 100 kilowatt installed. Electric efficiency higher than 50% is the control unit. Basically, no nitrogen oxide, no sulfur oxide, as I said. And yeah, so to save resources and reduce emission, this is the target that we have as a researcher for the future of energy. And this is one way to reach this type of target. Yeah, so I concluded here. I hope to be in time. So, of course, thank you, and thank to the Fuel Cell and Hydrogen Joint Undertaking that has financed this very interesting experience.
Thank you. Thank you to Massimo Santarelli for this very interesting presentation of a big pilot project on an industrial sites plant. You said is one of the biggest plants in Europe. So I think you clearly showed which were the results of this project, and very honestly, the challenges that still need to be faced to guarantee the market access of this kind of solutions. Okay, so thank you again. And going to the next presentation, we go from a European funded project to a regional funded project. The Clean Drone Eye project is an example of a project realized with the contribution of the regional funds of Piedmont Innovation for Innovation, which our region dedicates to research and innovation projects of cluster members built and implemented also with the role of the clusters in terms of screening, evaluation, and scouting of the most potentially innovative project ideas. All the I believe all the project partners in this project were from Piedmont region. So I give the floor to Carlo Luetto from Tecnodelta for the presentation. Thank you, Carlo.
Hello, good morning, everybody. Thanks again to Environment Park for giving me the opportunity to present my project. I will share the screen. Okay. Could you see my screen?
Yes, can you put it in? All right.
It's okay, it works.
Mm-hmm.
Okay, so I will present this project that is a project that we did with the three partners here in the Piedmont region. I will go through just a small indication of what we are now going to make as a research activity. This is the research activity of our company. So since 2007, we are involved in activity related to the hydrogen use. We work a lot in the hydrogen storage and the possible use of the hydrogen with different technologies. So in this case, we have work with metal hydrides, and we decide to put on the market this the project that the name is Clean Drone Eye. Because we did this experience and we put a lot of things that we learned during the year with the hydrogens. So the aim of this project was to demonstrate the feasibility of manufacturing a drone complete with the hydrogen production system and a refueling station. Here you can see just a drawing of the project. So the idea is to use alternative energies to produce hydrogen with electrolyzers. Then we have a system to compress the hydrogen that is produced, and at the end we can put the hydrogen inside of a tank that is installed on a drone. The partners. So the project is a collaborative project financed by the Piedmont region. The partners are quite small companies, and we have also the involvement of the University of Torino. So I'm talking about as a project coordinators. I am a part of Tecnodelta. We were in charge to make the production and refueling station. Then there was another company that the name is Stones that was in charge to build the hydrogen drone, complete of the fuel cell. And then another company, a very small company, that was Microtex. It was in charge to make the electronic management of the fuel cell. Then at the end, in the project, the University of Torino with the chemical department was in charge to studying the compression system with innovative technologies to make tests of these compression systems and to make the LCA of the system. Going in detail, so as I told you, the idea was to test the complete chain from the production to the use. So starting from the production with the electrolyzers, then we put in place a small purification unit in order to have the good quality of the hydrogen to feed the compressor. The compressor we put in place is a compressor done on 2 stages. The first stage is with innovative compressor with metal hydride systems, and then we have a booster in order to reach the maximum pressure to charge the hydrogen tanks. And then the idea is to have a very easy way to charge, to change the tanks on the drone itself. Here you can see the pictures of the drones that we did. In details, this is the system that we built. Starting from the left side of the system, we have all the control panels of the complete systems. Then we have the production unit with the electrolyzers connected with the small tanks of demi-waters. Then here you can see the cartridges of the purification unit. Then the hydrogen goes in this side of the system. That is the first stage of the compression that is done with metal hydride compressors. This is quite innovative system to compress hydrogen. This is a way to compress without any movement parts. So it means that we have only 2 reactors. The hydrogen comes in, and then we will see after how it works. At the end of this stage of compression, that is the one with metal hydride, we have gas boosters. That is a commercial one. That is high-driven boosters, and then we have here at the end of the chain the hydrogen vessels. That is the one that is on the drone itself. The electrolyzers. So the production is standard electrolyzers. Is with a delivery pressure of 30 bars. The power supply could be with the photovoltaic system, as we saw in the first image, or can be, of course, directly connected to the grid at 220 volts. Then at the end of this system, we have a purification stage with a cartridge with zeolite system inside. Then at the outlet of the electrolyzers, we have this first stage of compression. Here you can see the complete performance of the compressor that is made of metal hydride plus boosters. We reach a flow of 150 normal liters per hour. We have filled a cylinder of 3 liters of capacity. This is geometrical capacity, and we reach as maximum pressure 300 bars. Here you can see an image of the hydrogen compressor. Here you can see the monitoring of the pressure of the first stage reactors and the second stage reactors and the temperatures. Now I will going to show you how the compression works. That is really quite simple. So we, as I told you, we use metal hydrides. We have 2 reactors inside. We put metals inside of the reactors. We have a thermal fluid that is around of the reactors. The hydrogens comes inside of the metals. We have the thermal fluid that keep the temperatures under controls. And in this phase, we are in the absorption phase. It is the one that we have at low temperatures. So if we have a look here, we can see in which point we are. So we are at this point here during the absorption. So hydrogen comes. We have the phase transition in this phase, and then we have the complete filling of the reactor in this part of the curves here. Then once all the reactor is completely filled with the hydrogens, we can increase the temperatures inside of the system, again with the thermal fluid, and then we have the hydrogen desorption. So we move from this point, to this point here, and we have the hydrogen release. So as you can see here, from this point A to B that are this here, we can move to this point, yes. And so we have a stage of compression. As I told you, we have two stages. The first stage is has an inlet pressure of 30 bars and the outlet pressure of 130, 140 bars. And then the second reactor has an inlet pressure of 140 bars and an outlet pressure of 220 bars. So it's a quite innovative systems. We have no movement part. The only part we have is a pump that is used to drive the thermal fluid. And we have heaters to heat up the fluid, and we have a cooler to cool down the thermal fluids. The metal hydride reactor is a tubes in which the alloy is put in. We have porous filters inside just to avoid the powder to go to outside. The dimension of the two reactors, first stage and second stage, are the same volume. As I told you, we have two stages. The heat exchangers is incorporated. We have the thermal fluid that comes here in this part of the reactors. And of course, we put inside of the system some sensor to monitor pressures and temperatures of the systems. Here is the pictures of these metal hydride compressors. So it's quite small systems. We have the reactor 1 here. We have the reactor 2 here. Here we have the buffer of the hot fluid. Here we have the buffer of the cold fluid, and then simply two pumps that gives the thermal fluid to one reactor or to the other reactors. At the outlet of the system here, we have the connection with the booster. As I told you, there is a standard gas booster. We have compressed air to drive the boosters. The pressure that comes inside of these boosters, 220 bars, and outlet pressure, we have more or less 300 bars. That is the pressure that we have used to fill the tank. About the electricity production on the drone itself, we have used a PEM fuel cell. It is a standard one. This is very lightweight. We did an analysis on the market and we found that this one that is very useful because it is very lightweight, as I told. The gas supply comes inside of the fuel cell at 0.5 bar. We have a maximum flow rate of 16 normal liters per minute, and power supply that we have from the fuel cells is 20 volt, 4 volt CC. We decide to put on the drone two fuel cells of 650 watts each, and we have operative temperatures about from 5 degrees to 35 degrees. The fuel cell we put on the drone were two. So the company that was involved in the project, Microtex, was in charge to manage this electricity that were coming from two different fuel cells. So they developed a system in order to have the same load to the two fuel cells. It's very important to balance the load, not to have too much from one fuel cell to the other. And so they developed this electronic unit to manage this system. Here you can see a graph of one test that we did on the fuel cell, the two fuel cells coupled together. We have here the hydrogen consumption during the test. And then you can see in the red and the yellow the behaviors of the currents of the two fuel cells during the flight. As you can see, is quite equal. You have just a small difference in some point, but anyway, the electronic device that we developed, especially for this application, it works very well. This is a testing bench that we put in place just to test the system. During we did several tests, and we use for this test different loads in order to simulate the charge, so the drone itself. At the end here, you can see the drone that is the last pieces of the project. So we decided to use quadcopters. So we have 4 engines to drive the drone. The flight time we reach with this system is approximately 17 minutes. Working temperatures, so this is working temperatures of the drone. It depends, of course, the minus 20 is the lowest temperatures we can have on the system. When the system is working, of course. The power is 1.3 kilowatt, that is the 2 fuel cells connected together. We have, of course, hydrogen gas. The quantity of hydrogen that we have inside of the cylinder is 930 normal liters. The total weight of the drone is 11 kilos, in which the fuel cell is 1.3 kilo. The electronic unit we develop is 0.5 kilos, and the weight of the tank is 3 kilos. And we have possibility to have a payload of 1 kilos, and the rest of the weight is the frame. We also develop a system that has been developed from the safety point of view. That is a communication between the pilot and the drone. So from panels, we have the possibility to monitor the hydrogen pressures. So we have in time the level of the pressure, the charging of the pressure in the tanks. We have the monitoring of any alarm on the fuel cell. The fuel cell has the possibility to send an alarm. And then also we have the charge level of the emergency batteries, because from the safety point of view, we put inside of the systems an emergency batteries that is able to help the system in case of any troubles of the fuel cell to land in safe way the drone. Here you can see image of one flight we did with the drone. This is the drone how it looks like. We put inside of the system pressure regulators. The pressure regulators is connected directly to the cylinders or to the vessels. Here you can see also the pressure transducers that is directly connected to the cylinders that gives the quantity of the hydrogen that we have on board. And the time that we reach is 70 minutes with a maximum payload of 1 kilos. So more or less it was all about our system. Thank you for your attention. I'm available for any question you might have. Thank you.
Thank you, Carlo. Yes, you very well presented an example of customization of different components and optimization of different components for a very, very specific application, which is in this case drones. So very, very interesting. I think one question could be the exploitation of these solutions on the market, but this is a question maybe for the B2B session, if anyone is interested, or for the questions and answers. So don't forget also to use the possibility to make questions with your button question and answers on the bottom of your screen. So thank you again.
Okay. Thank you.
The next presentation. Making hydrogen affordable to sustainably operate everywhere in European cities. This is the title and the aim of Everywhere project, a demonstration to market project that will be presented by Stefano Barberis from RINA Consulting. With this very brief introduction, I leave the floor to Stefano, please.
Good morning, everybody. I'm Stefano Barberis from RINA Consulting. First of all, let me thank Luca, Julia, and the whole Environment Park team who invited me today to talk about Everywhere. Everywhere is a European funded project funded in the field of FCH-JU initiative, so in the field of FCH-JU joint undertaking, and that foresee also the participation of Environment Park among the key partners taking care of the supervision of the demonstration campaign. What is everywhere? Everywhere, as introduced by Luca, has the goal to make hydrogen usable and, let's say, visible to be used everywhere in European cities, particularly not for the, let's say, traditionally already explored application like buses, like the use of fuel cell and hydrogen in cars or in residential application, but in a very niche market that is the temporary power genset market, that at the end of the day could be an open entry market for hydrogen technologies. Also because, you know, it is very visible, it can make hydrogen technologies more you know, socially accepted and also let's say more affordable from a public perspective point of view. Indeed, the goal of the project, as I said, is to use the fuel cell technologies in temporary power application to fuel, for example, construction sites in our cities, music festivals, temporary events organized in cities, but generally speaking, therefore, to bring hydrogen technologies really, really close to people, towards the possibility to provide temporary power via a zero emission and zero noise solution. Indeed, in this moment, the temporary power application are mostly, let's say, are mostly covered by diesel gensets. And as you may imagine, diesel gensets have a problem in terms of noise, in terms of emission, etc. When we started this project in 2018, we indeed thought about the use of everywhere gensets, mostly in the sectors and in the application that I mentioned. But what we are experiencing and what we are living in these 3 years is that actually this type of technology have more and more interest, not only, let's say, from the event sector that is more and more attracted by sustainability, so is more and more keen to, you know, use and have a zero emission solution, but also, let's say, also by, for example, new sectors that we didn't take into account initially, like, for example, the movie sector that sometimes has to make sets in cities during the night, have a quite high amount of power required, for example, for lights, for effects, etc., but cannot use, for example, diesel genset because they are noisy and during the night can bother people living there. Therefore, you know, as I said, the main objective of the project is to realize 8 transportable gensets equipped with PEM fuel cell, 4 25 kilowatt and 4 100 kilowatt, integrated with pressurized hydrogen storage. This storage has the size of guaranteeing at least 8 hours of full power capacity operation. Generally speaking, the demonstration campaign, that is, as you can imagine, the main objective of this project, can be valorized, particularly not only for, can be valorized for other activities, like, for example, the evaluation of the logistic feasibility and the logistic campaign to transport here and there at this genset, the evaluation of the regulatory aspect, but also, for example, the evaluation of economic and business modeling to launch on the market these products. When we started this project, we saw since the beginning some challenges, like the fact that we are going to realize a first of its kind product realized by an orchestra of partners, and also the fact that, you know, for sure it was important since the beginning to identify what could be the main target market for the exploitation. I'm telling this because I know this event is very targeted on this topic. You know, for example, we soon identified the fact that there is no competition, unfortunately, between diesel genset and fuel cell genset from the CapEx point of view. But particularly looking at some specific market where gensets are used, for example, the short-term rental market that is mostly, you know, dedicated to provide power to events, in this type of market where the CapEx, so the capital cost of the system, is not so heavy, it's quite, it is possible to have a remunerative business model, also because at the end of the day, in the final cost to the end user of the genset rental, the cost of capex and the, let's say, amortization and depreciation of the cost of capex is really minimum part, because at the end of the day, the major part is the logistics, the shipping, the fuels, etc. And at the end of the day, in this type of contracts, for example, our Everywhere genset can have something like a higher cost of around only 10%, but providing a real added value in terms of reduction of emission towards zero and a reduction of noise and bothering. As I said, this is the first of its kind product that has been realized by an orchestra of partners, all together putting pieces of this puzzle, because we will see later that the gensets are really a puzzle. Among them, I would like to highlight the Italian value chain, because we have the chance to collaborate with really big firms in the hydrogen and power converter sector, among them Free, Linde, and Gemport, while the fuel cell subsystem is provided by PowerCell Sweden, and the hydrogen storage system is provided by Mytec. Here you can see also other key partners, like, for example, THT Control, who supported us in the mechanical integration of the solution. D1, which is Green Music Initiative Association, that is supporting us to promote the genset in the music festival, and Acciona, who will host in its construction sites some of our genset. But why Everywhere hydrogen genset can be more beneficial than other clean energy solution? I already said something. So the fact that, for example, if compared to diesel genset, of course, diesel genset have, let's say, an environmental and social acceptability, let's say, bias, of course, but at the same time, they are more reliable. They can operate in extended runtime. If we look at the current on the market solution, of course, the main competitor is a battery-based containerized system that, as you may imagine, has one main issue related to the extended runtime that, unfortunately, to replace and refill the genset can take so much time. So from this point of view, let's say that the fuel cell-based hydrogen system can be a sort of compromise between a battery-based solution that is clean, but at the same time have some bias, and the diesel one. In this sense, we started to think about also to guarantee an easier operation in terms of regulatory aspects. We started to think about how to structure our system, how to structure our genset, and we thought about having something quite easy to be installed, plug and play. So with, for example, a distribution socket panel very similar to the diesel genset one, and we thought to operate with a two boxes solution, one box related to the hydrogen storage and one box related to the fuel cell subsystem as it is. We planned and designed it on the paper. As you can see, it is divided in 3 rooms, one dedicated to the fuel cell, separated to the power converter one, in the middle with a room where the thermal management system is embedded. As you can see, we thought about it via render, but we already realized the 2 first prototypes that you can see in this picture, and that you can visit virtually, unfortunately so far, in our website, www.everywhere.eu, where you can make a visit of our genset. As you can see, we are talking about a more or less something between a 10 and a 20 feet container, very similar in terms, particularly in terms of distribution socket panel and interaction with the end user to any other type of diesel genset and on the market genset, and something that is easy transportable by a truck. This genset, the first box, is directly connected to the second box that is a bundle of pressurized hydrogen storage able to operate up to 525 bar and easily refuelable by a gas truck or even by even in presence of pre-cooling at an hydrogen refueling station. So where we are now, as you could see, we have realized the first 2 prototypes. We are currently realizing the following one and finalizing the commissioning test of the first 2 prototypes, because we would like to use them in demonstration, because demonstration is crucial. As I said, we will perform the first test in summer 2021. Unfortunately, let me say, due to pandemic situation, we couldn't start them earlier, but we are very motivated to start them since summer 2021. And that is purpose both Environment Park for the Italian events and Fundación Hydrogen Aragon for the Spanish event and the One Green Music Initiative for the music festival events are in this moment trying to build up a calendar for this summer demonstration campaign. Hopefully, obviously, that some events could happen and be organized due to current pandemic situation. So what I would like to say today is that it's very important for us to get in contact with you, not only to, know more about your interest, about our genset, but also to understand if you would be interested to use our genset in the next summer 2021, but even in 2022 and in 2023, because the project, as you know, will go farther up to 2023. So it's very important to contact us, not only, let's say, to host it, because to host the demonstration, but because, as I said, the demonstration is very crucial to bring to market our solution as soon as possible. We are targeting indeed the 2025, and we are motivated to do so because we are already receiving a lot of expression of interest. So please join us, contact us via our website, because as I said, there could be the possibility to host our demonstration support group, but also to participate. For example, if you are a public authority or a consulting firm or a research institution related to connected to cities, also to join our Everywhere Cities working group that is also studying, thanks to ICLEI support, how to facilitate from a regulatory point of view and a policy point of view the use in European cities of our Everywhere genset. Here are some activities that we are doing thanks to the Regions and City Interest Group with ICLEI. So please, if you would like to join us, get in touch with us, follow us on the social media, follow us on our website. And if you would like to host a demonstration, feel free to contact both of us in RINA and in Environment Park. Thanks a lot for your time.
Thank you, Stefano, for your presentation. You really showed very clearly that unfortunately, environmental advantages of technologies like hydrogen technology do not mean automatically that these technologies are used and are widely used and applied. So, and this does not mean that all barriers are automatically solved. You clearly talked about social acceptance, regulatory barriers, economical aspects. So this is why, for sure, the identification of entry markets for hydrogen technologies and demonstration, as you clearly told, is very important, and demonstration is a crucial step. On our side, we can confirm that from our observatory, private and public organizers of events are really interested on this possibility. So we hope that we will soon see the first results of this demonstration project. Thank you.
Thanks to you, and also thanks for your support in this phase, particularly on the regulatory aspect that is, as you said, quite complicated.
Okay. So going on with the next presentations, the demand of technologies related to the exploitation and production of hydrogen is increasing, and this means that the number of devices and equipments that we need to be that are used for this purpose is increasing, and at the end of the cycle of this equipment, we will have, and we are having, issues related to waste management. This will require a sustainable approach, and it's necessary to look for this. So it's necessary to explore processes that are able to recover and recycle the materials and components of these fuel cells and related technologies to give them new value. And this is why I leave the floor to Anna Marchisio and Henning Att from Ensel Recycling, which is partner in the Best4i project. Please, Anna, thank you.
Thank you, Luca, and thank you, Julia. I'm very happy to be here and to be your guest, offering a quick overview of something which is yet to come, because we don't have yet any industrial streams of fuel cell scraps, but perhaps in 10, 15 or 20 years, we will be in a different situation and we want to be well prepared. So I will also share my screen now and open my presentation. I hope you can see it.
Yes, just put it in full screen.
Yes,
All
that's
right.
it. Okay. So again, thank you, and thank you for attending. Just a few words about the company I represent here, the Hensel Recycling Group. It was founded over 20 years ago. We have nowadays 7 subsidiaries, both in the EU and abroad, and 1 joint venture in China. Our services go from purchasing to toll refining, and we are one of the world leaders in spent auto catalyst recycling. That, together with other kinds of scraps, such as e-scraps, are our core business. Hensel Recycling holds different certificates from ISO 9001 to the more recent approved 45001, which is the Occupational Health and Safety Certificate. Back in January 2021, we started a project together with a consortium made of other 7 entities from 5 different European countries. The project is called Best for High, and one of its goals is recovering different materials from exhausted fuel cells and reusing them for new products. This project would last 36 months and has been financed within the EU Horizon 2020 program. As a recycling enterprise, we do care about environment and are proud to contribute to CO2 emissions reduction. I offer to you in this slide an overlook of the total quantities of ounces of PGM, platinum group metals, extracted through mine production and also recycled, including the jewelry branch 2 years ago. We see that we are talking about big numbers. And in the second part of the slide, you see also how many platinum group metals were needed and coming from the recycling of spent auto catalyst and are needed to produce new auto catalyst. We made a small contribution to this recycling, and you can see it here. It is equivalent to 11 tons of precious metals that we recovered, mainly platinum, palladium, and rhodium, from exhaust catalytic converters. This, of course, reflects in a reduction and economization of the overall CO2 emissions, because, of course, the secondary recycling of precious metals also produces emissions, but they are largely inferior to the ones produced by the primary source. And this is equivalent approximately to 150,000 tons per year of CO2 less. Coming to the topic of today, I would like to offer you an overlook about the chances which the market hopefully will provide for recyclers of fuel cell components. Okay, So in this first slide, you see some market data concerning megawatts and shipments in divided by global region in 2017. The key growth application in megawatts terms is clearly transportation. Toyota had a very aggressive politics with 1 million of fuel cells electric vehicles target, and they plan to use the same stack in heavy duty systems. Hyundai similarly has a 700,000 system goal, and Honda is also moving quickly ahead. So Asia is dominating in this scenario. Europe shows its main producers like Daimler Chrysler introducing a fuel cell electric vehicle plug-in battery hybrid, and BMW is a little bit more cautious, moving towards fuel cell electrical vehicle deployment. But between these regions, there is a full supply chain from catalyst through to recycling, and European players, in our opinion, may find it hard to gain a stronghold in these regions. As far as fuel cell scraps are concerned, Europe is occupying a very small share, as you can see, but electrolyzers may be a bigger European opportunity going forward, we think. So a fuel cell contains many more materials, including several different plastics, as well as adhesives, silicones, rubber compounds. And at its heart is a catalyst-coated membrane, which predominates, though some products have catalyst-coated gas diffusion layers as well. While the recycling of spent catalysts involves mechanical separation of metal and ceramic parts, grinding into powders, sampling, etc., the fuel cell requires that a complex part containing several different layers, which have been joined together with a very strong glue and sealants, be deconstructed and the various parts sent off in different directions for reprocessing. And it bears many similarities to processing batteries, or even more so electronics, so we scrap. However, the PGM content is much higher on many systems that would be found in e-scrap, for instance, in mobile phones or in computer motherboards. So it is this part of the fuel cell stack that contains the PGM catalyst and gives rise to the essential performance of the system. So it may be necessary to process with the unit at least partially intact. In this case, there will be several streams coming from processing, including a Nafion dispersion and an ePTFE layer, carbon GDL materials, titanium field mesh, for instance, for some producers at least, and the PGM itself. The upshot of all this is that the recycling process will be very different to what it is practiced today. And we think that new relationships, partnerships, and expertise will be required to stay inside this game of processing automotive PGM. So it will take some time for this to be put in place, and the best time to begin is now. That's one of the reasons why we are here today with you. In the next slide, I am offering you an overview again of regional markets. In this case, Europe and North America are observed. Asia, as we have seen before, dominated shipments in 2017 with the almost totality of the production, and Europe is very much ahead, at least in terms of megawatts. But it is true that in megawatts terms, Europe has always competed for the lead with North America, who enjoyed almost half of the fuel cell market by megawatts areas. Asia sat in the second place with 45%, although its actual production share is higher, and some of which is being exported. Coming to the recycling opportunities within regional perspective, well, the figures we have published so far relate to domestic sales, but exports from Asia are increasingly significant, especially towards North America and to a growing degree also to Europe. And this is very important for us because from a recycler's perspective, the country of shipment is important for production scrap, but the country of sale more so for recycling. So in the country where these produce are going to be sold, we have the most chances to come into business with the end companies. On this basis, the vast majority of opportunity currently lies outside Europe. Many of the stationary projects are based on PAFC, whereas in North America, the deployment of SOFC seems to dominate. Therefore, the Asian region has opportunities for PMG recyclers, both in PEM, fuel cells transport units, and PAFC stationary units. I must add, perhaps, I should have said it before, that we at Ensor Recycling are actually focusing strictly on PEM products, because being our industrial core, the recovery of platinum group metals, we are not interested in technologies that do not bear precious metals to be recovered. So our focus is a little bit a tunnel focus on PEM fuel cells, as we see from this other slide. So we see here a projection from 2012 up to 2017 of the shipments in units and in megawatts and in kilowatt per unit shipped. And we see that the peak of the shipments was reached in 2013. Coming towards 2017, we have numbers which are considerably less than the peak level of the last 5 years. However, we think this is not so significant compared with the exponential growth in the megawatt shipments, which reached 487 megawatts in 2017. As you can see, it is steadily increasing. The average kilowatt unit has rose tenfold between 2012 and 2017 to reach 10.7 kilowatts per unit, undoubtedly boosted by the 100 kilowatt typically needed for a passenger car. That is the standard for passenger cars. Important for us as recyclers, the amount of platinum on a PEM is directly proportional to the power output. And therefore, a higher amount per unit is a positive factor for recycling economics and revenues. And I think my colleague Henning Hoot will be able to give you a better explanation in the B2B session about what is profitable and what makes sense to recycle. Well, I think this slide is very simple. The PGM value dwarfs and minimizes the other components. Platinum is worth 1,000 times more than cobalt, for instance. And we tend in our strategy to stay focused on the recovering of the PGM, trying to avoid disposal costs for other components. And this is why it is very important, it is essential, paramount to find good connections and good networkings for all other components that may be recycled or destined to other uses without having unnecessary waste production. Right. I think the previous slide is even better explained by a present. It is clear that we need a route to sell, for instance, cobalt, as it is unavoidable when processing transport MEAs. And we hope, and it looks like there might be a strong future market for the recycled naphthalene. The recycling of naphthalene is one of the things we are focusing on the Best for High project as well. A partnership with a company that has that supply chain could be a big advantage. A partnership that, for instance, has a good knowledge in solvent separation for this goal to be attained. And approaching the recycling of whole stacks and the fee calculation of treatment based on disposal costs to third parties is, of course, mandatory. Alternatively, one should avoid stacks and only accept disassembled scrap MEAs. But as a whole recycler, we see it is difficult sometimes to discriminate and to say, no, we only take this. You know, I mean, of course, we need to have a strategy for that. But now we are, let's say, training a lot, and we are training with full stacks, preferably. So my last slide. In the end, I think we should be optimistic, but with feet rooted into reality. Because while large stationary equipment stacks will possibly have a very high total platinum content, between 1 and 2 kilo, in our experience, there are relatively few, and they have very long lifetimes. I mean, I must say, luckily, because they are made to last. Rail and marine are also long-term, but are similar to large stationary. So I think a similar kind of strategy could be followed with those items. And small stationary units may have only 1 kilowatt fuel cells. So in large numbers, we were reading 250,000 installed only in Japan, but with minus than 1 gram of platinum each. And the same goes for UAV, unmanned aerial vehicles. These are unlikely to be profitable in our view. However, they may need the MEA recycling process to avoid environmental hazards, and being perhaps the go-to MEA recycling experts of any type, that could create very strong business opportunities. Last but not least, electrolyzers are possibly an opportunity to watch closely. As I said at the very beginning, we talk about starting market around in 10 years from now, more or less, because we don't see it coming before that, if not in very small streams. And the biggest nearest term opportunity is in heavy trucks and buses, because they are likely to be the applications that are going to be used at the earliest, as you can see here. We have, this is very, I mean, easy for main areas of business opportunity. And the first one, as I mentioned before, is represented by heavy-duty mobile systems. The second, stationary applications. The third, electrolyzers, and the fourth and last, fuel cells electric vehicles. So, I mean, passenger cars are going to come at a later point in our view. Yes, I hope I added a glossary because some of the terms are not perhaps so known. Right, and this is my contribution for today. I think my colleague Henning will be able to give you more information as far as the business opportunities in practice are concerned. I've seen that there are 2 questions. Perhaps
yes,
at the end, yeah?
Yes, Anna, thank you. I also have seen 2 questions. I will close with the presentations, and then we have some minutes to take the questions and give the answers. Thank you very much. You really make a very complete presentations of what's happening on the market, both at international and European level in terms of devices. And recycling opportunities connected to this market. Also, if not in the short term, but for sure, also, I think your message was these recycling opportunities open the possibility to create also new value chains, new market, and that will require skills and competencies for this. And so be prepared, I would say, to what is going to happen in the next years in the midterm. So thank you. The next presentation is not exactly about a project, but about a technology transfer initiative. I was when I see the presentation, I was quite surprised to discover that there is a potential matching of nuclear fusion derived technology and the technology demand of different sectors. One of these is the hydrogen related sector. So Lorenzo Dall'Oro from RINA Consulting will tell us something about this interesting fusion technology transfer program. Thank you, Lorenzo.
Thank you, Luca. Thank you for inviting me and giving me the opportunity to share about this opportunity. So, do you see correctly my screen? Okay.
Yes.
So today I'm going to present our activities currently going on concerning the technology transfer from nuclear fusion to many other sectors, including the hydrogen one. Just a few words on my company. RINA is a global firm based in Italy, but with offices all over the world, and active particularly on compliance services and on consulting engineering across different sectors, including the ones you see on the right.
Excuse me, Lorenzo, can
yes.
you try to, can you just push on the display settings and duplicate presentation so that we see the full screen?
Okay, sorry. Yes, I can just. No. Sorry, just trying to stop share. Sorry for this. Maybe now it's better.
Now it's okay.
Okay, sorry. So RINA, as I was saying, is active on these sectors. RINA is also active since many years in R&D project. I reported, just to mention them, the projects currently running on the hydrogen field everywhere, and Best4I already presented during this webinar, but also Flex and Confu and Spotlight. But the focus of today will be our technology transfer activities. This is one of the services we actually offer to our customers, and particularly my business unit, Materials, Technology and Innovation. In our Total Innovation Management services, we support companies from idea generation through the scale-up of their products, and within the idea generation, we use also these portfolios of technologies identified in the nuclear field, but also in other fields, to identify possible technologies and possible solutions. Starting from the experience we had with the European Space Agency, we were for almost 20 years technology brokers for them. We developed a methodology for technology transfer, and we adapt this type of methodology to the fusion sector. Basically, there are two large technology transfer activities going on. One for Eurofusion. So Eurofusion is a large organization, a large consortium that include almost 30 research organizations and universities all across Europe, and develops, supports and coordinates fusion research activities on behalf of the European Commission Euratom program. On the other hand, the Fusion for Energy is a EU organization managing the European contribution to ITER, so the world's largest fusion experiments, that is building a large tokamak in Cadarache in the southern France. So based on these large networks of organizations and companies, we are able, with the support of a network of brokers or all around Europe, to map the technologies that are developed in this context, and to select the ones that could be potentially transferred to other sectors. So we developed a sort of portfolios of technologies based on the knowledge gained in these two large research programs. On the other hand, we collect from the companies, the research organization, the needs they have, their technology needs, and with a mediation and a matching, trying to find possible synergies and opportunities with already identified technologies in order to define the path to transfer effectively the technologies from the fusion sector to other possible sectors. First of all, I would like to give you an overview of the portfolio by Eurofusion. We have more than 50 technologies and services available for technology transfer by Eurofusion. We cluster them across these 5 sectors: sensors and characterization and diagnostic technologies, advanced modeling, data processing, and simulation tools. Then we have the materials, the technologies for hydrogen and gas, and finally, energy and power transmission technologies. As you can imagine, the research and development that fusion is facing is very, very important, and many breakthrough technologies need to be discovered, researched, and there is a huge potential for these technologies to be applied also outside fusion. The same has been done for fusion for energy. The categories are very similar. Here we are speaking of very high TRL technologies because all of them will be installed in the ITER running machine. So these are very high TRL technologies, and we're in direct contact with all the technology providers providing this type of solutions. But why hydrogen is related to fusion? The fusion reaction that is inside the ITER tokamak reactor will be powered by the 2 isotopes of hydrogen, deuterium and tritium. The fusion of these light hydrogen atoms produce a heavier atom, so helium, and 1 neutron and a large amount of energy. So you can see here on the right the closed cycle in which the deuterium, tritium, so the fuel of the reactor will be used. As you can see, the tritium should be separated from the flow, recovered, and then supplied again with the deuterium to the reactor. As you can imagine, a lot of engineering research is going on, and a lot of results should be transferred to the hydrogen sector. I'm going to just give an overview of some example of fusion-derived technologies that have already been used for the hydrogen domain. As I said, decades of international cooperation among major research institutes on these topics, a lot of effort on R&D, and a strong technical background. Some example of fusion-derived technologies include selective membranes to separate hydrogen that are used in the ITER machine to separate tritium from the fuel flow, but also sensors to measure hydrogen partial pressure, libraries to study the dynamics of hydrogen transport and the modeling, a lot of software for simulations, materials that need to withstand with such demanding and extreme conditions, and also components, valves, tubes for able to withstand with these conditions. I'm going to show you some of these examples with a little more detail in the next slide. We selected among the technologies the hydrogen permeation barriers developed by Jülich Research Center based in Germany. So basically, barriers that are deposed with a method of deposition through a magnetron sputter deposition device. This allows to obtain a very interesting property of these layers of coating, providing high thermal stability and very low permeation to the tritium in this case at high temperature and pressures. This is the first example. The second one, transport libraries for hydrogen transport modeling. This has been developed in Spain by Empresarios Agrupados in close collaboration with CIEMAT. These are basically modeling softwares able to study in details and simulate the processes involving hydrogen flows. Then we have Italian technologies by INEA, sensors to measure hydrogen partial pressure in liquid metals. This was developed for the fusion sector, but were, for example, already transferred to other sectors such as solar thermal plants. The last one, probably the most interesting one, are palladium silver membranes developed again by INEA. These membranes are realized in bulk metal and were developed for the separation of hydrogen isotopes from tritiated water. They were applied in a project to the hydrogen production via reforming of methane that was obtained from biomass. So these membranes allow to obtain very high purity hydrogen and to obtain very high yields thanks to their selectivity, and used within this system via reforming of methane allows to produce very high purity hydrogen to feed high efficiency PEM fuel cells. This is just one example of success story derived from the collaboration between a fusion derived technology and an industrial company that actually, in collaboration with INEA, developed this type of application. So, as you see in the previous slides, there are many technologies, many solutions that have been identified. You can have a look at them on the websites. I reported the links in the previous slides that will be shared after the webinar. There are a lot of potential behind these technologies, so do not hesitate to contact me, to contact us, check together the portfolios, identify together possible opportunities. Thank you for your attention.
Thank you, Lorenzo, for your presentation. Also, thank you for reminding us the importance of technology transfer, and I would say also the importance of the cross-sectoral technology transfer, because this is also an example of cross-sectoral action leading to use of innovation. There are some. Okay, Thank you again. There are some questions, but I see that we have the time to give answers at the end of the session. Okay, moving to the next presentation. We already heard in our second webinar about the skills and the research competencies of the University of Turin on hydrogen storage technologies, not only, but in particular on this. And the iCare project is developed a hydrogen storage tank with the use of a solid state hydrogen carrier, linking hydrogen and its storage. So I leave the floor to Professor Marcello Baricco for the presentation about iCare project. Please, thank you.
Yes, thank you, Luca. Everything is okay?
Yes.
Yes. So thank you very much for giving us the opportunity to present the results of the iCare project. Because of this web-style seminar, I'm used to present myself at the beginning, just to say that, as you said, I'm working at the University of Turin, and at the moment I very much engage with the fuel cell and hydrogen joint undertaking, because I'm working in the scientific committee of the FCAJU. So for this reason, I just like to remind to you what are the key points of the FCAJU that's actually supported a lot of those projects that has been presented today. And what I like to stress is that basically for the FCAJU, Europe is putting the money, but industries and research centers are playing together to work in project. And I think this so-called public-private partnership is a very good approach for promoting the exploitation and the implementation of the new technologies. Okay, so FCAJU, maybe you know, is engaged in very different topics and both related to the production, to the use of hydrogen in production, in transport, in the heat, electricity, the matter related to the critical raw material, and of course something related to the grid balancing. The pillars of the FCAJU are related to energy transfer and cross-cutting, and today I would like just to stress something related to the energy itself, and in particular a point related to the hydrogen storage for renewable energy integration. This is one of the main goals. There are a lot of projects, and this is basically the scheme of FCAJU related to the production and storage, and there is a specific goal related to this aspect. So this topic, as Luca was saying, is very much considering our own university, and I like just to stress that the storage is just a step in the whole hydrogen value chain, but in some sense is quite crucial either for handling the hydrogen that is produced by electrolyzer, but also to be delivered to the hydrogen refueling station. So in our university, we have several departments that are engaged in the whole value chain. And today I would like just to stress what has been done in this specific topic. So when we talk about hydrogen storage, basically there is a series of requirements. And of course, one point is the high gravimetric and volumetric density. Of course, gravimetric is crucial for transport and volumetric is crucial for stationary applications. Of course, it's quite crucial to have temperature and pressure that are rather close to ambient conditions in order to avoid any trouble in managing. Of course, the system needs to have a very high number of charge and discharge cycles. And of course, everything has to be done quite quickly, and it has to be safe and possibly quite cheap. So at the moment, the approach of storing hydrogen is basically related to the three different approaches. The first one is simply to use the compressed gas. This is an example of a tank that is used in transportation for cars. But of course, the compressed gas is the standard approach for storing hydrogen. The second approach is to use a so-called cryogenic liquid, let's say to put hydrogen at a very low temperature. This is very good because it is able to produce very huge amount of storage, but there are a lot of energy efforts for obtaining that. That is the same for gas, because for compressing you need a lot of energy. So one possible solution that is followed in this project is to use what we call carriers. Simply to have some materials that can be solid or liquid, where hydrogen can be sticked and then can be taken back in a second step. So for this specific matter, the FGHAU in 2018 put out a topic that was actually related to the use of hydrogen carriers for the stationary storage of excess renewable energies. What is important in the call, there has been a lot of important points that I will discuss quickly in the following, but this is just to stress that quite often the call actually have very clear goals, and it's quite important in the project to be very stick to the goals that are required by the call. So in order to try to answer to the question from FGHAU, we put up this consortium that developed these hydrogen carriers for renewable energy storage project that is called HyCare. And the goal was to try to answer different questions. So what, and again, the goal, sorry, is to combine hydrogen carriers with the phase change material. I will come back later in this point. Why? And the main point is to try to reduce the footprint of the system that needs to be used for storing of renewables. And the goal is to try to put carrier in large-scale applications. And who is doing that? Basically combined research centers with companies. And the idea is to perform a sort of test system in Paris, in the living lab of ENGIE. And the goal, of course, is to provide this test for industry, for companies, but also for regions and cities. And of course, the goal is to demonstrate that it's working and then to be exploited in the future. So this is basically the consortium. We are coordinating the project. What I like to stress, we have a couple of big companies. ENGIE is a very big French-based electricity companies, energy companies, and GKN is a company related to the powder, metallic powder. We have Technodelta. They already presented the project today, and another small medium enterprise in Germany. And then we have different research centers, including Environment Park, that is hosting this meeting. HyCare started at the beginning of 2019. The plan was to close at the end of this year, but we will likely have an extension of at least 6 months. So what are the main goal of HyCare? The idea is to demonstrate that with a carrier, actually you could store up to 50 kilos of hydrogen, but this can be done at very low pressure, let's say lower than 50 bar, and at rather low temperature, lower than 100 degrees C. So the combination of these 3 parameters is the main point of the project. Of course, the idea is to have a low footprint, to have a sort of innovative design, and the core of the goal of the project is to combine the hydrogen storage with the thermal energy storage. I will explain this later a bit more in the detail, but this, I would say, is the real innovation of the project. Of course, the system had to be demonstrated to be very efficient, to be quite well integrated in between an electrolyzer that is producing hydrogen and a fuel cell that is using that. And of course, that will be demonstrated in a real application. Safety will be an issue. And of course, as all other projects, we will have some techno-economical evaluation and an assessment of the impact, and to exploit possible application, and of course, to disseminate the results of the project. But let me go to the core of the concept. The idea is to have your tank that is containing a carrier that in this case is a metal hydride. You have hydrogen coming in. When the hydrogen is getting into the metal, it is producing heat. And this heat, instead to be dispersed, it is stored in a phase change material. So the heat is there. And then when you need the hydrogen back, you basically use the heat that has been stored in the phase change material, and you provide this heat to the metal hydride, and because it is receiving this heat, is increasing its temperature, and then it is delivering hydrogen. So at the end of the day, you are combining the two, and the efficiency is very much improved. From the technical point of view, the idea is that with a metal hydride, you basically have pressure and temperature, And when you have a low temperature and high pressure, you have an hydride, so hydrogen is stick to the metal. But when you have a low pressure, high temperature, hydrogen is out, is in the gas phase, and the metal is alone. And of course, you need to move from one side to the other, playing together with pressure and temperature. And when you do this, this step, at the end of the day, you are having a change in heat. And this heat is what is taken by phase change material, simply because it is moving from the solid state to the liquid state. That is what is clear in theory. In the real life, actually, you have to manage that. You have to play with some changes, both in temperature and pressure and in enthalpy. And this is a challenge for the project itself. But the key point is basically to combine these two approaches. So let me quickly just show what are the final scheme of the project. The idea is to combine the hydrogen storage based on carriers with the heat storage, and this is linked with suitable fluids. And of course, the idea is also to get heat from the electrolyzer or to the fuel cell when you produce or you use hydrogen, and of course to have also an external source of heat that can help the efficiency of the wall system. So this is basically the scheme. So let me quickly describe the different steps of the project. At the beginning, the matter was to get to find the right carrier. We decided to work on the titanium iron system and playing with different suitable substitution. This is an example we played in analyzing possible substitution with manganese and copper. This is a typical pressure versus capacity, what is called PCT curve. And the idea is to find the right pressure and temperature conditions in order to find the goal, to reach the goal. Well, when the alloys, the material has been selected, we were able to go up to the industrial production. And in order to store 50 kilos of hydrogen, because the gravimetric capacity of this material is not far from 1 weight%, it means that we need at least 4 or 5 tons of this powder. So this stones has been prepared and has been analyzed in the lab in order to check the quality of the powder itself. One of the key points was to find the right condition, and this is what we call the window based on both temperature and pressure. And at the end of the day, this window has been defined, and this window is in between 30 bar and 2 bar, and with the temperature that is lower than 70 degrees C. And this is definitely helping in improving the safety of the wall system. The other key point is to be sure that the system is working with the hydrogen that is coming from the electrolyzer, and this has been checked in comparing the cycling on the system with both clean and what we call dirty hydrogen, so with some impurities inside, and everything was okay. So basically we were ready to start with the design of the system. The idea is the system to have it inside of the standard container, but in order to go to the very final system, we start in designing a prototype that has been already tested. So the prototype was a sort of subunits of the final system that was using both iron titanium based alloys and the PCM with about this amount, 60 kilos of alloys and about 30 kilo of PCM. So this prototype system has been designed, powder has been combined in suitable pellets. This is the tank for the metal hydride, and this is the tank using the PCM. And the two tanks have been connected one with the other, and it has been tested up to now, and it is perfectly working. So there is room for moving to the final system at the big size in order to reach such a goal of 50 kilo of hydrogen. Okay, of course, the system is now ready to be concluded. In the meantime, we are investigating possible exploitation, and I'd like just to remind the European community is providing a lot of support for such a kind of approach. We are using such a kind of exploitation supports, and the new one is called Booster, but this is a very interesting point for support from Europe. And on the other side, of course, there is a sort of analysis of the techno-economical approach for the world system, comparing this technology with others, and then to compare with the possible impact in the environment, performing what we call the life cycle assessment. And let me just conclude that we are ready to disseminate, to communicate our projects. So please, if you are interested on that, contact me or try to have a look in LinkedIn, in Twitter, or other opportunity that we have for this point of view. Okay, Luca, basically I can stop here, and then I like to thank, of course, my collaborator at the University of Turin, and of course all the partners that are engaged in the project spread in Europe. Thank you very much, Luca, and to all the people for attending this presentation. Thank you.
You're welcome. So thank you for having showed us the interesting outcomes of this project and the results, and also for having briefly explained the approach and the objectives of the FCH joint initiative undertaking. As you said, is funding most of these projects and many others which are relevant for evolution and for the future of hydrogen technologies. This is very, very important to be known. So the last presentation for today, we focus on a specific technology, which is reversible solid oxide cells, and a particular project, the REFLEX project, where Environment Park also, which is the technology park where the Clever cluster operates, will host a non-field demonstration of a particular application of this technology, integrating the energy produced by a mini hydroelectric plant, which is located inside the area. So thank you, Jonathan Moriet from CIRFEN. I leave you the floor for your presentation.
Okay, thank you very much. Do you see my presentation?
Still not.
No. Sorry, I seem to have lost you. 1 second. Do you see the presentation now?
No, still not.
What about now?
Yes.
Okay.
It's okay. Thank you.
Okay, so thank you for having me. Thank you, Luca and Giulia, for setting up this webinar. I'm happy to present about this specific project that CIRFEN is part of amongst other consortium members. So we're using a reversible solid oxide cell, which is a type of technology that is quite recent. And we're using it specifically as a stationary application on buildings. So our buildings are an important part of the energy transition. They consume roughly 40% of the energy in Europe and are responsible for 36% of emissions. So at CIRFEN, we're a startup that is involved in accelerating this energy transition through the use of storage for renewable energy and using hydrogen and hybrid technology. So we want to make buildings responsible for their own energy. So as much as possible that they produce and consume the local energy. But of course, in the form of renewable energy is a lot of time is intermittent. And so you have issues to deal with that. And we're trying to offer solutions to make the national grids more resilient by increasing the flexibility. So at the heart of the CIDFEN technology is this reversible solid oxide cell energy processor, which acts as a two-in-one electrolyzer and fuel cell, essentially. So it's 100% reversible technology. I think in a lot of the presentations that we've seen so far, we were either looking at fuel cells or electrolyzers. This is really a two-in-one component, just depending on the way the electricity is flowing and whether we have energy, hydrogen production or hydrogen consumption. In both cases, so in electrolyzer mode, there is where you are consuming the electricity and there is a storage and heat and the production of hydrogen. And in the fuel cell mode, so the two modes are obviously, they're not running at the same time, it's one or the other. In the fuel cell mode, there is the production of the electricity and heat. The CIDFEN was based, is a startup issued out of the CEA, which is a public research institute in France. And we've been in existence since 2015. This is a diagram to show the interaction of our main product, which we call the Smart Energy Hub here at the center of the screen. So on the left, you have the end users of the electricity or the energy. So which in the form of buildings, or it can be sites, campuses, hospitals that have energy needs in the form of electricity, heating and cooling, and more mobility, whether electric charging or even hydrogen. And the Smart Energy Hub kind of sits itself at the intersection of all these energy flows. So ideally, you have a local on-site production of renewable energy, mostly in the form of solar panels, but as we'll see, it can be small wind turbines or small hydroelectric plants that provide directly energy to the building, and any surplus will be stored in the Smart Energy Hub. So the Smart Energy Hub, as presented before, is made up of three core components. One of them is the reversible solid oxide cell that I presented earlier. There is also a battery component. So we use lithium-ion batteries and use basically the advantages of the batteries and the energy processor and get rid of the inconvenience of both. And we also have hydrogen storage tanks, which are installed on the outside of the building. There is still the connection with the traditional grids, the electricity and gas grids, in the case that we still need to consume from the grids. And there's also the possibility to export any excess energy back onto the grid. We are talking about an energy storage solution. So this is to show an example of when the solution would be needed and when it wouldn't be needed. You have in blue the building consumption, so the electrical building consumption throughout a regular week. We're talking here about an industrial building, for example. Monday through Friday, you have an electricity consumption, and on the weekends, they're not working. And then we have three scenarios of solar panel installations. So this is to showcase that in the red curve, you only have, you barely have any surplus. So the production of the solar production is never really above the consumption of the building. So you have a very small amount of surplus to be stored. So it's not really a case where we would need an energy storage solution. The yellow curve is showing that there is storage need only on the weekend. And the ideal solution is whenever you have storage during the day, so the peak of the sun around noon, 2 p.m., where you would be storing all of this energy, and then using it, giving it back to the building in the form of a fuel cell and the battery at night whenever the building is still consuming, not as much, but still consuming, but there is no renewable energy production in the case of solar panels. So there's a need for storage depending on the various amounts of production. In a nutshell, how our smart energy hub works is that when the building generates too much energy, so here again, solar panels, but can be any type of renewable energy, the building will consume as much as it can directly from that energy, and energy surplus will be stored in the battery, which is in blue here, and in the energy processor, so converted into hydrogen. At night, we have the opposite, or whenever there is not enough energy that's being produced, and the batteries and the hydrogen will give the electricity back to the building, as well as heat for the energy processor. So we combine it, it serves as a combined heat and power to maximize the efficiency of the energy that is produced. A specificity of our technology is that whenever the hydrogen storage is fully used and there is no more, the smart energy hub is still capable of working with natural gas or biogas, which would be even better. So the gas is fed through a reformer in the smart energy hub and then feeds directly into the energy processor. And so out of the gas, we're still able to run in a fuel cell mode and provide the electricity and heat to the building. So therefore decoupling from the traditional electricity grid. So that obviously adds fuel flexibility and reduced downtime for the building. I've been talking about buildings, I talked about an industrial building, but we're really looking at all types of buildings, at least over 1,000 square meters. That's the current offering we have today, between 1,000 and 10,000 square meters, whether they're existing buildings or new buildings, various types, office buildings, residential, industrial. Any entity that needs to consume energy during the day in the form of electricity and heat. And the current offering we have today is for those sizes, but we are working on a new development of the product, which will address buildings or more campuses that are above that 10,000 square meter limit. So more universities and hospitals that have larger energy requirements. So to go into details a bit more about our actual product, this is a view of what it looks like on the inside. They kind of look like electronics cupboards. This was from our prototype. This is a description of the various specifications for the product. So as I mentioned, we do use lithium-ion batteries. That is more to have a high responsiveness to whenever there is energy demand, peak demand, or high energy storage. So we use 50 kilowatt hour modules for batteries. It's completely modular, so we can put one module just like we could put 5 or 10. For the hydrogen storage, we use a simple B50 kilogram bottles that store 1 kilo of hydrogen each, which is compressed at 200 bar usually. And on the energy processor side, so as mentioned, there's two modes, the electrolyzer and the fuel cell mode. Whenever we're in electrolyzer mode, so therefore storing the energy, one module of our energy processor will store up to 40 kilowatts and produce around 800 grams per hour, as well as 4 thermal kilowatts of energy. So that is again for one module. Our smart energy hub is completely modular from the the battery level, but as well the energy processor and the amount of storage that we put. So we really, I'll show through the tools that we developed internally. We really work on a case-by-case study and see what is the best size for the Smart Energy Hub and install it based on the client. On the fuel cell side, we're a bit lower on the what we can provide in electrical power per module. So we're at 6 kilowatt in electric power and 4 in thermal power. So that's what we would be giving back in fuel cell mode to the building using hydrogen. This to give a quick overview of Sylphen. So these are we're situated between in the Alps between Grenoble and Chambéry. We've been around since 2015. We're about 18 to 20 today. These are the 3 co-founders, and I'm going to talk more about the project and specifically the one that we're interested in here, the Reflex project. This was our proof of concept that we worked on with NG Lab in 2018 in Paris. This was when we validated several aspects of our technology. So through the electrolyzer, the production of the hydrogen, the compression and the storage, the coupling with the batteries. We have an internal energy management system that we developed that was controlling the system, controlling command strategies, the different piloting that we can do, and the remote access of it all. These are the signed projects that we have today. We have one residential building in Monaco, another one which is the headquarters of a distribution system operator in northern France. And then these are 3 projects that we're currently working on right now, 2 of them being in Italy that were financed and subsidized by European funding. And specifically, we're looking at this Reflex project in Torino. The Reflex project stands for Reversible Solid Oxide Electrolyzer Fuel Cell for Optimized Local Energy Mix. So it is based at ENVI Park in Torino. The aim of that project is really to look at how high of an efficiency and flexibility we can operate our Smart Energy Hub, looking at obviously the cost implications of running all this with our technology. We will have different operational strategies as well that we'll be testing throughout the duration of the project. As I mentioned, we need renewable energy. I mean, it can be used with any type of electricity, but we prioritize renewable energy at the site of ENVI Park. So there is a 16 kilowatt PV plant. You have a picture there. And then you have also a hydroelectric plant of 670 peak kilowatt power. Both as part of this project, the renewable energy from those 2 production facilities will feed, any surplus will feed into the Smart Energy Hub that will be installed and give back the energy to the headquarters of ENVI Park, which is that I believe that building at the back, which is what it looks like on campus. This Reflex consortium, so of course there are many partners involved, and so we've listed them as part of the different tasks that they were dealing with. We had the CEA, Elcogen, and DTU in Denmark looking at the fuel cells and the stacks. So I believe Elcogen was providing the fuel cells for the energy processor. CEA was looking at the integration and the stacks, and DTU was running the simulations and the testing through computer analysis. We had GP Tech and the Universidad de Sevilla looking at the system power electronics. So the batteries, the AC-DC converters, DC-DC converters, and the basically anything dealing with the powers. The VTT in Finland was looking at the whole system modeling and the interactions between the fuel cell, the energy processor, and the batteries. Sylphen, we were charged with designing and manufacturing the actual solution, which was integrating all those different components. NV Park was providing the site and welcoming us to install the technology on their building and looking and doing some of the testing on site. And we had ENGIE, so the French energy supplier, looking at the economic aspects and the market analysis. So it was really a true collaboration between all those different actors. I'm not going to spend much time on this slide, but basically we developed internally some models to reconstruct energy profiles on buildings, which is the Profitbat software. We have ConfigDim, which analyzes the perfect sizing for the solution, and that's kind of the result that we give to clients or partners that we work with. Specifically to the NV Park and the Reflex project. So we were given only monthly and annual data for the energy consumption of the site. So you see that they use electricity, biomass and natural gas, mostly for heating and cooling and domestic hot water. We had the information for the energy consumption, the surface, and therefore the kilowatt hours per square meters. And had some indications about the various buildings. Through that Profitbat software, we were able to reconstruct the hourly profiles of those different buildings and see what that looked like. So there on the right, you have in green is the energy production, and in black is the energy consumption of the site. And you see that, for example, as I mentioned before, these are moments when you have excess energy production over the consumption and are moments where you should be storing the energy. This is more, below is more what it looks like on a weekly basis. So this is over the course of a week, you see the consumption is most of the time lower and the production higher. So therefore there is a need to store the energy. This is what happened when we ran it with our ConfigDim software to look at what is the proper sizing and how much renewable energy sources we should input into our system. So we had 3 scenarios where we take 25% of the renewable energy on site production, 30% or 50%, and look at what the numbers that it gives us through the Smart Energy Hub. We can see that with the 30% renewable energy, you do have a slightly less overconsumption, self-consumption, but you have more, the overproduction is the surplus that needs to be stored. But you can see that if you go too high, then you have too high of a number that is the surplus that needs to be stored. And if we are not able to store it, then it's kind of needs to be re-injected into the grid and you might be losing there. The other important factors here is with the 30%, we're using 44,000 kilowatt hours that are produced from the hydrogen that is produced on site, as opposed to if you were going on a bigger scenario, then you wouldn't be producing as much from the hydrogen. We are reducing the amount of electricity that we buy from the grid, and that's really the goal here, so that we can reduce the CO2 emissions from the site. So this is just a comparison with the graphs that we see here on the right, and yeah, we're looking mostly at the environmental impact, economic, and energy autonomy of the site. So these are 3 different and important criteria that we look at whenever we do our analyses. We, at the moment, are in the phase of deploying our technology on site. So this was us visiting the campus. Of course, we were, like everyone else, affected by the pandemic. And so the goal is to go with a 30% renewable energy production. We will optimize the contribution from the hydrogen production and lower the gas purchase from the grid. And that is also the highest energy carbon reduction while using the highest amount of green hydrogen that is produced on site. We're still refining the piloting strategies, and we're working closely with the partners on site, including Dr. Sabina Fioro. And these are just pictures from whenever we went there. We brought the French crepes that we couple with Italian Nutella, and we're hoping to have a great collaboration on this project. That's the end of my presentation. I do work closely with Mario Lamagna, who is our Italian contact for this project, and who is also working on that Procida project. So if there are any questions specifically with regards to Italian regulations, I would highly recommend you get in touch with Mario. So that's the end of my presentation.
Okay, thank you, Jonathan. You also showed some pictures of Environment Park. That's where we are hosting these webinars these days. So the participants had a small opportunity to make a virtual visit of our site. Thank you. There is I've seen that the speakers already answered to most of the questions raised by the participants. There is a last one from Francesco Mezzera for Professor Baricco. The question, if you are here, Marcello, is it possible to have some more information regarding the coupling of thermal storage with the hydrogen storage? Example, expected technology coupling, heat sources would be suitable, size limitations, and so on. I think it's a quite huge question. I don't know if you want to take more time and use the B2B session, or you want to.
Yes, I think you're right. That is not is a question that is not easy to be answered in few minutes. Let's say that at the moment the main goal is to demonstrate a concept that coupling metal hydride with phase change material is possible, because there has been up to now a lot of estimation and simulation, but they have never been demonstrated. So in some sense, this is the big goal of the project. And then how to extend and to improve the efficiency, of course, is a matter to tailoring and to optimize the design. But happy to discuss on that in B2B session.
Okay, so as Marcello said, I share again the link for the B2B session. Of course, we would like to offer all the participants and speakers a coffee break, but we have to wait for better times, so that's it. We have time for a short break now. I thank all the participants and the speakers. This is the link to access the B2B session, which will be open from now to 1 o'clock. And I will leave the slide here so that you can have the link in front of you. And I'm gonna say see you later. And of course, don't miss the next webinar next week on Wednesday morning again. And thank you very much for your participation.
Thank you.
Thank you very much.
Thank you.
Thank you, everybody.
Thank you, everybody.